So, welcome everybody. My name is Maximilian. I will be presenting the burning bottle cutter experiment on behalf of the Switzerland team from ETH Zurich. The problem statement is the following. Is it possible to cut a glass bottle in two pieces with a string using fire and cold water? What is the physics behind this effect and how can one optimize it? Is it possible to cut out a shape in the glass that is more complex than a simple straight line? Now, I set myself different goals to analyze this experiment. The first one being to develop a theoretical model. The second one to create an experimental setup to verify this theoretical model. And the third one to determine optimization possibilities. And lastly, I also tried to develop an experimental setup to cut complex shapes into the glass. So let's go ahead with the theoretical model. This one is a bit much in the beginning. So we start from the free energy of the glass bottle. Since the glass is an amorphous medium, we can treat it with continuous mechanics. From continuous mechanics, we take the free energy and then apply Hooke's law to the free energy to get an expression for the stress tensor. The stress tensor is a tensor of second order, and it can be understood as giving the sigma here is the stress tensor, and it can be understood as giving the force into a direction, into an area direction of the body. And the epsilons are the deformation tensor, which gives us a measure for the deformation of a body. And here in the k and t minus t0 is the expression for the temperature deformation. And here the T0 is a reference temperature, so it's important to think of it as in thermodynamical processes, more or less. That you say, okay, we start at a reference temperature T0, and then if we move in a process to a temperature T, that is our deformation or tension we get due to the thermal deformation or due to heating our glass bottle. Now we go into the development of the model. I assumed that I can treat the bottle in a Cartesian coordinates just to simplify the math. And basically, I justified it that I can imagine basically wrapping up the cylindrical part of the bottle as a plane. And the second assumption was that the temperature, when I wrap the string around the bottle and light it on fire, that the ensuing temperature distribution is a Gaussian distribution. Now, I come to the development of the theoretical model. I modeled the process of the free heating as heating without any stress on the bottle. Therefore, the stress tensor is 0. And this leads to the fact that I can get an expression for the deformation tensor here, since the tensor with the subscript 0 is the diagonal entries are 0, and therefore I have a deformation from the heating with the Gaussian function. And now comes the important step of the sudden cooling. I stated that because of the sudden cooling, the deformation of the heating is still present. And additionally to that, we have a second term, which is the Tc, the contact with the cold temperature, which adds an additional deformation from the cooling. And this results in this expression here below. This is our tension in the bottle after we heated it and placed it into the cold reservoir. It is proportional to the hottest and coldest temperature, and you can also see it's not uniform, the stress distribution, since it's also depending on the Gaussian function of the temperature distribution in the beginning. And now I wanted to find a condition that justifies if my bottle breaks or not. And for that, I turned to the concept of the ultimate tensile strength, which basically is a measure for how much force per area I can apply on a bottle until it breaks at a certain point. For glass, this value is given by 33 megapascal. And that is basically my condition for whether my bottle breaks or not. And as you could see from the model here, basically the point where it should break is at the maximum of the temperature distribution, because there it will be the first place to reach this critical tensile strength. Now we come into the experimental verification of the theoretical model. For that, I first had to build myself a good temperature sensor, which I could place on the bottle to measure the temperature in a good way. For that, I calibrated a steel wire where I measured the resistance and heated it up to certain temperatures, thus giving me a function for the temperature of the resistance. Here you can see the function. It's quite a linear relation, and that gave me my temperature sensor. This temperature sensor I used in this following setup. Here I have a constant voltage source, and I measure the current. Thus, I measure the resistance by Ohm's law. And here it's a bit tough to see. I have the same steel wire I used to calibrate my temperature sensor. I have it. And this is basically, I will wrap it very tight around my glass bottle around the string to measure the temperature directly at the glass bottle. And down here, I have my cold reservoir where I control the temperature via a thermometer, such that I always can precisely determine my cold reservoir temperature. Using this experimental setup, I got the following results. My theoretical critical temperature, which the bottle has for that it breaks, is 448 Kelvin. And you can see here, I marked the temperatures for which the bottle broke in red and the temperatures for which the bottle didn't break in blue. The theoretical model is a slight overestimation, but there's more or less a clear edge where the bottle should break or not. And I did this experiment for different kinds of glasses. And here's another type of glass. And here my breaking temperature was in the same magnitude. It was 538 Kelvin, and here, but it's again a slight overestimate. And while I was doing experiments, I also took wine bottles, and there I investigated how different shapes and not shapes, sorry, but different heights of the burning string on the bottle affect my measurement. And here I can see a slight tendency that it's better, that I need less temperature, therefore less tensile strength to break the bottle, if I place the bottle not in the middle of the cylindrical part of the bottle, but at the end, at the top end and at the bottom end of the cylindrical part. This gives me a hint that maybe pre-existing tensions inside the bottle can play a huge role, and these can be described by beam theory, basically adding an additional stress from a bending beam to the temperature stress I developed before. And now I come to the third goal, which is describing the optimization possibilities. And the first optimization possibility would be to increase the temperature difference between the burning string and the water. The second one is to improve the heat conduction from the burning string to the bottle, because this is definitely a place or an aspect where a lot of energy loss and therefore can occur, and therefore I could avoid an overestimate of the critical temperature. And furthermore, that I could increase the complex total stress across the bottle if I add additional cooling at other parts of the bottle. And for the theoretical model to improve it maybe and to avoid overestimates, it could be also good to determine material properties myself. And further investigation into the pre-existing tensions inside the bottle would also definitely help to give a more accurate model, and also to investigate the impact of different burning string heights. And lastly, we come to the fourth goal, which was where I tried to investigate whether it was possible to cut complex shapes. And here I unfortunately have to state that it was not possible for me in my experimental setup to cut complex shapes in a controlled way. However, sometimes when I placed some parts of the string not as thoroughly across the bottle, or I tried something new, I was able to get shapes like you can see on the right, where different breakings occurred and different shapes. And what I think could be reasons for this behavior is that the complex pre-existing tensions cause these breaks or already micro cracks or something like that. For that, it would be also good to investigate the pre-existing tensions or maybe micro cracks inside the bottle. Thank you for listening to my presentation. Here are my references, and I am looking forward to this discussion part.
So thank you, reporter, for the interesting presentation on the question of burning bottle cutter. And my name is Yan Sheng, and I'm from the UK team, and I'm going to talk about some of the points which I think are important in this problem, and I hope that we'll have an interesting discussion later on. So first, as a summary for the presentation from the reporter has started the presentation with a very thorough theoretical model analyzing the temperature of the bottle due to the burning wire and how the stress in the bottle evolves due to changes in the temperature. And then the key part of the theoretical model, discussing the fracture, the reporter used the ultimate tensile strength to do the analysis. And then after that, after the theoretical formulation, the reporter gave a very good experimental setup and generated some very good data and some agreement with the model can be seen. And after that, the reporter also gave a qualitative discussion on how the bottle cutting can be optimized, and I find that very interesting. And finally, the reporter gave some discussions on their attempts to cut complex shapes, though in the end, that is difficult. And I do agree that cutting complex shapes will be very difficult. So overall, I think the reporter has given a very nice presentation, very clear discussions, and very good experiments. And for a bit more details, I'm going to talk about the strengths and weaknesses for the report. So the first thing is that the theoretical model is very rigorous, and the reporter made good use of continuum mechanics, using concepts like free energy, stress tensor, and Hooke's law, which are, of course, very applicable in the scenario here. And also, the reporter has done a very good job in spelling out the assumptions. For example, the reporter has talked about the assumption that he treated the bottle surface using a Cartesian coordinate. Although strictly speaking, there is some curvature, but I believe that the reporter has given a very good argument why this curvature is unimportant by considering the learning skills which we are interested in. And also the reporter also talked about the temperature Gaussian distribution, which is good because this is an implicit assumption which may be important later. And in terms of the experimental side, I really like to commend the reporter on being able to measure the temperature using a custom thermometer. We know that measuring the temperature of a burning wire is not easy. And the reporter has successfully used a resistance thermometer, if I understand correctly, to measure the temperature of the wire, and that's and I would really like to comment on that. And I also think that the reason why the reporter can get decent experimental agreement is because they're able to measure this temperature fairly accurately using the custom thermometer they have built. And after that, speaking of the comparison between the experiment and the theory, I think in the theory side, the reporter has done a good job in elucidating the temperature dependence for the breaking of the bottle, and this does compare pretty well with the experiment, and there is some reasonable agreement. Things are roughly on the same order of magnitude, and the trend is clearly correct. So I would like to congratulate the reporter on being able to succeed on that. And finally, towards the end, the reporter also made some analysis on the geometry dependence for the cutting of the glass by considering the placement of the wire on different positions of the glass. Although this is not specifically asked for during in the question, I think this is an interesting point. And I really liked the discussion which the reporter has brought up. So these are the strengths. However, I think there are also some areas of improvement. And I think the main problem is that, and the main problem I have with the report is that I think the treatment of the fracture using ultimate tensile strength is not really appropriate in this scenario, and we do need more detailed fracture mechanics to analyze the problem. And this is something which I would like to discuss in more detail during the discussion. And also, we could see that there's some disagreement in the result in slide 13 and slide 14, and there's also some inconsistent result. For example, in the range where most of the bottles do not break, some bottles can break, and we would like to discuss why that could happen. And I think going beyond the ultimate strength, the ultimate tensile strength model is going to be fairly important in explaining those behavior. And finally, not finally yet, as another point, the failure to cut complex shape is also related to this treatment about ultimate tensile stress, and I think we could potentially suggest some method to cut complex shape if we consider the fracture mechanics in more detail, and we would like to talk about that later. And finally, I think time dependence in the model could be important, and that could be a potential discussion point which we might want to go into. Okay, I think the time for my speech is up. The first point on the ultimate tensile strength. So ultimate tensile strength is usually applied to metal, and in this case, we're dealing with glass. So what type of material do you think glass is? Is glass a brittle material or is it a ductile material?
Glass is definitely a brittle material.
Yes.
And therefore, it is possible to determine a value for it, but it's still possible to determine a value for the ultimate tensile strength. However, as you pointed out, the consideration of already pre-existing micro cracks or stuff like that is definitely important.
Yes, I would like to confirm this point. Indeed, glass is a brittle material, and for brittle material, it can undergo very limited inelastic deformation. And for ductile materials such as metal, the reason why we can have a very well-defined ultimate tensile strength is that whether a fracture or crack can propagate depends very much on how much elastic deformation we get at the crack tip. And that's a very definite value. It's not so dependent on how sharp the crack tip is or how many micro cracks we have. And in contrast, in glass, when we're talking about the creation of new fracture surface, the energy required is actually very little. So crack can propagate very easily if there is an existing crack tip. So in this case, the ultimate tensile stress is not going to be very well defined because it's going to be extremely dependent on the surface condition. For example, if your surface is rougher, there will be more micro cracks, and then it's much easily, and the cracks, the propagating fractures can be initiated, and the propagating fractures can be initiated much more easily. And with different surface textures, the ultimate tensile strength can vary a lot. It can vary across different orders of magnitude. And as a very quick example, we can think of things like reinforced glass. The glass are reinforced by introducing a compressive stress on the surface to prevent those cracks coming up. And just by this surface treatment, the ultimate tensile strength can be increased by probably at least one order of magnitude, I think.
I agree on that. Sorry.
Yes, yes.
I agree on that. I just chose the ultimate tensile strength as a first starting point to get an estimate in which order of magnitude I am working in. And as I could show with the experimental data, I managed to determine that I get to this order of magnitude more or less precisely, in which the bottles are breaking. And the thing is why I didn't work those micro cracks so much into my theoretical model is because they can vary quite a lot from bottle to bottle, and therefore I would need to do profound analysis of the pre-existing micro cracks for basically every bottle I break before. And as you're right, I should do that. And it would be definitely the point to continue this theoretical model more. But I just, due to time constraints, I didn't develop it until today. But I thank you for your input, because that's definitely also the point where I see the most improvement necessary.
Yes, I would like to I think indeed analyzing the surface can be quite difficult. But I would like to just provide some potential methods for surface analysis. For example, simple microscopy, just under optical microscopes, can give some information about the surfaces. And this could be important in the experiment because if the surfaces are in different conditions, that could lead to quite different ultimate tensile stress in the system, and that could potentially lead to experimental errors. So in terms of experiment, I think in the future, it might be useful to check the bottle by inspection under optical microscope for micro cracks before you run experiment. Mm-hmm. Or we could potentially go into the other extreme, which is to control the surface cracks. For example, we can sand the surface to create deliberate micro cracks and make it consistent across the runs to improve the repeatability of the data. And also, this also leads to a point that's related to the cutting of the complex shape. So as we have discussed, this surface fracture plays a very important role. And with the existence of a surface fracture, the fracture tip can propagate very easily. So if we can guide this surface fracture in a way by making indentations on the surface of glass, it might help you to cut complex shapes. So for example, you can use a knife to make indentations.
Actually, I agree on that, and I did that qualitatively. However, I did not manage to find the right depth of the crack to apply to the bottle. So basically, every time I tried that, the bottle just broke diagonally and uncontrolled, in not a controlled way. So I think it might be also worth to start with a better quality of glass, because now I just took glasses from the recycling bin, but maybe if I would try this more thoroughly, I should invest a bit more money maybe and buy a more good quality of glass, and then I can really control the depth of the micro crack. I control the strength of how I apply the micro crack. And then I could also see that working, because in fact, I tried some experiments where I created a crack on the bottle, and sometimes the temperature needed to crack the bottle seemed lower, but I didn't quantify it. That is, I should have done it. That's true.
Yeah, I think these are all related to the surface structure.
Now other team members can join the discussion.
Yeah, and then yeah. So as an add-on point to the cutting of the complex geometry, so one thing you have mentioned is that sometimes the glass break diagonally in a direction which you do not want. So this is of course related to the surface micro cracks, and that can actually be controlled in some ways. For example, you can use tape you can use tape to tape up the region where you do not want the crack to propagate into, and this tape will actually in some way help to protect the surface and prevent the micro cracks from opening up, and that might potentially help to improve the result. So that's just
that's an interesting point. Yeah, thank you. I did not think of that actually. Yeah.
Yeah. And then one last point is about the temperature dependence in the model. So there's no explicit discussion in the model in terms of temperature dependence, but do you want to briefly outline the different time scales in the model, which might be important here because we're, let's say, doing something like crunching here. So time scale might be important. So could you just give a bit of discussion on this point?
Yes, actually, if you would allow me to share my presentation again, I did not do any experiments on that myself, but I looked up some literature to that. And I have the following graph I can show in a second here. If it wants to work, yeah. Exactly, here you can see, this is basically the time evolution of the stress tensor. It's from an experiment actually from your university in Cambridge. On the left axis, you see the tensile strength denoted in a dimensionless way. And here you have the time evolution multiplied with the thermal conductivity divided by the area of your glass. And those different parameters, it's basically the Z divided by H, is a measure for the position where you are. So how far you are away from the source of heat. And as you can see, the closer you are to your source of heat, the higher the ultimate tensor, or the tensor, not the ultimate, sorry, the tensor strength is in the beginning, and then it decreases by time. And the further away you are from the heat source, the less drastic is the change.
Okay, so we can already see, so if we look at a plot, I think there's already something that's quite important at the bottom. So we have capacity divided by H squared, and if I understand correctly, this H has to do with the thickness.
Yes, exactly, yeah.
So we have a characteristic time scale for the diffusion of the heat into the bottle, right? So if you compare the burning of the wire versus the quenching, how would the time scale for the burning of the bottle, the burning of the wire and the quenching compare to this time scale?
Sorry, could you repeat this question?
So we have a time scale defined by H squared over kappa from the heat thermal diffusion, right? So this time scale, if we compare this time scale with the time required to burn the wire and the time required to quench the bottle, how would they compare to each other?
Ah, yeah, okay, I see, thanks. I would say that the time scale is bigger than the time it takes for the heat to transfer from the burning wire to the bottle. So we transfer the heat quicker than it to the bottle than it distributes within the bottle, I would say.
Right. So maybe one add-on question. So when the bottle breaks, what do you think the main temperature gradient is? Is it along the depth or across the surface?
Okay, that's actually an interesting question. It actually depends whether you break your bottle or whether you use a hot to cold reservoir or a cold to hot. If you break it, basically the crack propagates along the thickness of the bottle. So you start on top of the surface and then you move inside the bottle or to the center of the material. And that is for the case where you move from a hot temperature to a cold temperature. However, if you move from a cold temperature to a hot temperature, then the crack starts to expand inside of the bottle and then to move outwards of the outwards. Yeah.
So could you explain how you heat the wire in
During the experiment? For the calibration, you mean?
Well, not for the calibration, for breaking the bottle. Could you explain this process, how you actually break the bottle?
Yeah, okay, sure. I have a cotton string, basically, which I tie around the bottle, and then I make a knot in it. And then I take the string off, dump it into lighting fluid, and soak it in lighting fluid. Then I put it on the bottle, light it on fire, let it burn for a certain amount of time, and then I rapidly dump it into a bucket of cold water. And then the bottle breaks or does not break.
Okay, thank you. What is the burning temperature of this lighting fluid? Do you know this?
No, unfortunately not. But I don't know if it is that important to have a theoretical value for that, because the value I'm interested in is not specifically the burning temperature of the fluid, but of the mix of the fluid with the cotton string. Therefore, I think it's more important to determine the temperature of the burning string on the bottle than just the burning temperature of the fluid itself.
Okay. Then, sorry, one more.
If you have more
question
questions, you can maybe ask after.
Do I have more questions, or I should pass to another jury?
Yeah,
So-
let's. Yes, please, Leandro.
Yeah, I have a question.
Yeah.
Did you observe a separation between the point where you burn your lightning fuel and the crack and the break point? Because you assumed, I followed the discussion, but you assumed that it's almost coincident with the place where the wire is placed or where the fire is. But perhaps the maximum stress is not aligned with it. It's not at the same place.
Yeah, that's an interesting point. Wait, I can get some bottles I burned in a second. Because I'm actually in the room where we did or like in the room at university where we had, yeah. Exactly. Exactly, no. Yeah, exactly.
Yeah, like this. Yeah.
Exactly, but the thing is, it really depends. For example, here it's a bit higher. And then for this one, it is more or less directly at the point where I had the wire.
Yeah.
I think sometimes I also didn't. I think, for example, for this bottle, this was one of the very first, and here I was holding the bottle a bit diagonally while I burned it because I was afraid I would burn my hand. And then the heat was more spread towards, or the flames were more burning upwards, and then thus heating a bit more this part.
This does not show in your model, does it?
Yeah, that's the thing. Yeah, that's true. Yeah.
Okay.
Very much, Leandro. These other jury members has some questions.
Can I ask, can you go to your plot where you plot these bottles which were broken with respect to the temperature?
This one or this one?
Yeah, both are fine. I'm wondering why you have one. It's what do you think is the reason why? I would expect there to maybe be like a temperature after which all the bottles maybe break, but you have like this broken bottle in the middle of quite a few unbroken bottles, and so is it just like once that happened, or is it something that you can maybe model, or you know why it might have happened?
I think that actually goes back to the discussion I had with Yasheng. I hope. Sorry. I hope I.
Yes,
pronounced it
that's
right.
right.
Okay. Exactly. That pre-existing micro cracks in the bottle, they affect the breaking conditions very much. So, for example, I could imagine that this point here at 475 Kelvin was, for example, a bottle which had already pre-existing micro cracks, and thus it was easier, or thus less heat was needed to crack the bottle. Whereas most other bottles were more in a higher temperature. And as you can, and it more like you can more or less see the straight cutoff, but you always have some bottles which had micro cracks and thus are above or below where they should have not broken or should have broken or not broken, but they did the other thing.
Okay, thank you.
More questions?
Well, maybe I ask a question. Did you think about replacing the burning whatever it was, cotton with just another wire that you use as a controllable heater. I understand it's not like within the problem itself, but it's a way to study the system experimentally. More,
yeah, actually,
more
yes.
flexible. Mm-hmm.
Actually, yes. Basically, it would be the reverse of the setup I did here with the determination with the resistance. I could have also done it the other way around. Did I just place a conductor around the bottle and then control the current through it? However, I decided in the beginning for safety reasons to just do it with a lower voltage and to do it like that. And I was also afraid that people would say, okay, if I didn't use a burning string, did I really answer the task? That was also one of the motivations why I didn't do it with the voltage.
Mm-hmm. Okay, thank you.
And maybe someone very short question, if some
Yes,
remembers.
a very quick question that I wanted to ask anyway. The
Short,
glass
okay.
seems to have a set of melting temperatures. So do you think the glass is melting here anyway, or it remains solid, but the crack is completely coming from the tension?
I don't think it is melting because I think it's really because of the, let's say, brittle nature of the glass. Because at the cracks, it's not really a smooth surface, but you really have sometimes some edges and some sharp edges and some stuff like that. So I would think if it would be melting, then I wouldn't have so many sharp edges or something like that.